Swayam Prabha. Digital India. Educated India.
Hello, I welcome you all in this course on refrigeration and air conditioning, and we will continue our discussion on refrigerants. In the previous lecture, we were discussing about the requirements of an ideal refrigerant. So, requirements of an ideal refrigerants can be classified as thermodynamic requirements, chemical requirements, physical requirements, and environmental impact of refrigerants. This is also very important. The last one is the most important nowadays. We will start with the thermodynamic requirements. Normal boiling point of refrigerant is very important. Normal boiling point is normal boiling point. Normal boiling point of a refrigerant is the boiling point at 1 atmospheric pressure, and in this slide I have shown normal boiling point of different refrigerants starting from R22, which is minus 40.81, to 600A, which is isobutane, it is minus 11.75. So, these normal boiling points decides what should be the pressure inside the system. If the normal boiling point is low, the system will work on high pressure, and if the normal boiling point is high, the system will be a low pressure system, and the pressure ratio in high normal boiling point will be more. And for this we will do some derivation, a sort of derivation with the help of Clapeyron equation. So, the Clapeyron equation, which is a derivative of Maxwell relation, the Clapeyron equation says that dP by dt, this is saturation is equal to latent heat lambda by temperature, saturation temperature Vg minus Vl. It is applicable for a saturation condition of any fluid. Now, here, because Vg is much greater than Vl, velocity of the liquid, the volume of the liquid is much less than the volume of the gas. So, this can always be neglected. So, regarding this, we will do one small derivation to find the bearing of normal boiling point on the performance of a refrigeration system. There is a Maxwell relation del P by del T at constant volume is equal to del S by del V at constant temperature. From this Maxwell relation, Clapeyron relation has been resolved, that is dP by dt at saturation state is equal to latent heat divided by saturation temperature and specific volume of vapor minus specific volume of liquid, and this is applicable during phase change. Now, specific volume of vapor is much larger than the specific volume of the liquid. So, this term can be neglected, and the modified form of this Clapeyron equation is going to be dP by dt, dPs by dTs is equal to lambda is latent heat divided by Ts and Vg. Now, here for Vg we can replace Vg by P over RT. So, dPs by dTs is equal to Ps lambda over R Ts square. The further arrangement of this equation will give dPs by Ps is equal to lambda dTs divided by R Ts square. Now, we can further write it in differential form as d natural log of Ps divided by d 1 by Ts is equal to minus lambda by R is equal to minus B. So, B is equal to lambda by R. Now, if you look at the theory of thermodynamic similarity, which gives a number Tauton constant. Tauton constant or Tauton dimension number, and that is equal to m lambda over Ts. M is the molecular mass of the substance, lambda is the latent heat, Ts is the saturation temperature. And now thermodynamic similarity theory says that the substance of the same group will have this Tauton constant as a constant, Tauton number as a constant. So, here in case of B is equal to lambda by R, if we replace R by universal gas constant, it becomes m lambda over R bar. Universal gas constant is same for all the gases. Now, it can further be written as m lambda over Ts multiplied by Ts upon R bar. Now, this m lambda over Ts is constant is equal to theta Ts over R. Now, this is constant, R bar, this is constant. So, B is a function of Ts. Now, regarding this equation, if we integrate this, we will get natural log of Ps is equal to minus B by Ts plus A. At 1 atmospheric pressure, this is going to be 0, natural log of 1 is 0. So, A is equal to B by Ts. So, A is again function of Ts. What do you mean to say here? If we draw a curve between natural log of Ps and 1 by Ts, high boiling point of refrigerants will have steeper slope. Low boiling point refrigerants will have a less steeper slope. Now, if we want to depict this on the same diagram between two temperatures, this is pressure. So, this is the slope of low temperature refrigerant, this is the slope of high normal boiling point temperature. This is TO and this is TK. This is TO or this is TK or high condenser temperature and evaporator temperature. Now, this formation helps us in deciding which refrigerant we should go for attaining the refrigerating effect. The high boiling refrigerants have high pressure ratio because the slope of this curve is high, and low boiling point refrigerants have low pressure ratio. Further, it can be concluded from the previous derivation that high boiling point refrigerants have higher latent heat of vaporization. Now, pressure during phase change is also important deciding the refrigerant, because if the pressure is high, suppose in the condenser, if the pressure is high, robust design of the condenser has to be made. Similarly, in the case of evaporator, if the pressure is very low, lower than the atmospheric pressure, then there are chances that air may leak into the system. On the same side, the specific volume of the refrigerant will also be very high. So, that will increase the size of the compressor. So, we have to be, there are many factors which decide that what order of pressure we should go into the condenser and the evaporator. So, in the evaporator itself, the pressure should not be very low, so that the specific volume of the refrigerant is high and the size of the plant is bulky. And the same time, if the pressure is very high, then robust design of the system has to be made, and that is also not desired, because the cost of the system will increase. Now, critical temperature and pressure. For any refrigerant or for any refrigeration cycle, if it is operating farther from critical temperature, suppose it is operating here. So, in this case, In this case, the COP will be higher. If we shift into the upward direction, in that case, the COP of the system will reduce. So, the refrigerating cycle should operate far away as far as possible from the critical point. Now, freezing point of the refrigerant has to be low, because if the freezing point is high, that will also cause problem in the operation of the system. Volume of suction vapor. Now, the volume of the suction vapor, regarding the volume of the suction vapor, we have to compromise. If the pressure in the evaporator is very low, the volume will be large. For handling large volume of air, for large capacity systems, centrifugal compressors are used. But the cost of compression increases. If we go for, again I am repeating, if we go for higher pressure in the evaporator, in that case the system will become robust and the cost of handling the vapor through the compressor will reduce. Now, coefficient of performance, if in a temperature range of 40 to -15, the Carnot efficiency is given 3.97 here, we can easily calculate that. That comes out to be 0.8 kilowatt of energy. So, we should have coefficient of performance nowadays, I mean as per the energy point of view, it has to be, for example, a window air conditioner. For window air conditioner, it should be approximately equal to 3.5. So, COP of the system is also very important in deciding the type of refrigerant we are going to use. Now, chemical requirement. The refrigerant has to be, first of all, chemically stable, and flammability should be as low as possible. It should be inflammable in an ideal case. The toxicity of, first I will discuss them one by one, then we will discuss in details. The toxicity has to be 0 in ideal case. It should not act with water, should not act with oil, it should not act with material of construction. Every substance is flammable to certain extent. I mean, totally inflammable, saying that the particular refrigerant is not flammable is not justified. So, there are classes of flammability, class 1, class 2 and class 3. Now, class 1 indicates that the flame propagation at 21 degrees centigrade and 101 kilopascal pressure, there is no flame propagation. That is class 1, that is safe. Lower flammability, limit of more than 0.1 kg per meter cube at 21 degrees centigrade and 101 kilopascal. Heat of combustion has to be less than 19 kilojoules per kg. These are as per the International Institute of Refrigeration data. Now, class 3 is lower flammability limit of less than or equal to 0.1 kg per meter cube at 21 degrees centigrade and 101 kilopascal pressure, and heat of combustion is more than 19 kilojoules per kg. So, there are 3 classes, flammability classes, class 1, class 2, class 3. Now, toxicity classes are 2 classes, class A and class B. A signifies the refrigerant for which toxicity has not been identified at a concentration less than or equal to 400 ppm. If there is no toxicity as the concentration of less than 400 ppm, then it is class A. And class B signifies refrigerant for which there is evidence of toxicity concentration below 400 ppm. So, 400 ppm is the borderline. So, if the toxicity is observed below the 400 ppm, it is class B. If the toxicity is not observed below 400 ppm, then it is class A. So, toxicity and flammability combinedly, they are classified as the refrigerant class A1, A2, A3 or B1, B2, B3. Here it is written that B3 is B is toxic and A is non-toxic, and flammability is 1, 2, 3, 1, 2, 3. I have already explained that. Now, chemical stability of the refrigerant is always desired. During the cycle, the chemical should or the refrigerant should remain chemically stable. The refrigerant should not act with water, or it should not be not only act with water, it should not be hygroscopic in nature, so that it does not absorb moisture during the cycle, and if this happens, this may hamper the performance of the system. Now, action with the oil, the refrigerant should not act with the oil. Some of the refrigerants which are hydrocarbons are completely miscible with the oils. Ammonia is not miscible with the oil, that is the issue with the ammonia. For R134A, since it is not miscible with the oil, oil means mineral oil, natural mineral oil. So, synthetic oil is used in case of R134A. Action with material, the refrigerant should not react with the material of the plant. Some issues are related with the ammonia because ammonia reacts with the copper. So, copper material is not used in ammonia in the refrigeration system where ammonia is used as a refrigerant. Now, there are certain physical requirements also for a refrigerant, that is thermal conductivity, viscosity, dielectric strength, heat capacity, leakage tendency. So, refrigerant should have very high thermal conductivity, viscosity should be low, it should have good dielectric strength because in a small capacity system refrigerants are used for cooling the cooling coil of the compressor also. So, dielectric strength has to be low for the refrigerants. Heat capacity has to be low. Heat capacity is sensible heat capacity, it means this value of Cp has to be low for refrigerant, as low as possible, and leakage tendency should be minimum, nor especially ammonia has leakage tendency, and odor, I mean it should not give any bad smell, otherwise odor is good because through odor you come to know whether there is a leakage of refrigerant or not, but the refrigerant should not have any odor in an ideal case. Now, secondary refrigerants I have already discussed earlier in earlier lecture, but I will like to explain here also that I have secondary refrigerants are those refrigerants which pick from the heat from the object and discharge heat to the primary refrigerant. So, for example, chilled water in a high capacity refrigeration system. So, chilled water in a high capacity refrigeration system, it picks heat from the building or different parts of the building and discharge that heat to the evaporator or the refrigerant in the evaporator or primary refrigerant. So, this is the function of secondary refrigerant. Even brine in ice making factories, brine is also used as a secondary refrigerant. Now, ozone depletion. Now, a number of it was noticed in 1887 that CFCs are damaging the ozone layer and causing the hole in the ozone layer, and they are contributing towards the global warming as well, but the damage of ozone layer was the main concern. And regarding the ozone layer damage, there were certain myths also, like volcanoes and oceans are causing ozone depletion, as the volcanoes are the real source of atmospheric chlorine, not CFCs. This was propagated at that time. CFC is heavier than air, so they cannot reach the ozone layer. But the reality is, few volcanoes are strong enough to penetrate the stratosphere. Not enough volcanic activity to account for ozone depletion. No sudden jump in the volcanic activity that matches the observed ozone depletion. Volcanic chlorine drains out with the rains, and there was an example also, some data were collected at Mount Pinatubo, which where the stratospheric chlorine was not increased after eruption of this volcano. So, it was later on it was established, fully established that not later on, I mean it was established earlier also, but because there were some issues regarding the depletion of ozone layer by the chlorine coming from the oceans, but it is confirmed now that CFCs are depleting the ozone layer and their use is banned throughout the world. The manufacturing of CFCs has been stopped since 1996 and it is totally removed from the market. Now, new refrigerants have come into the market. Out of these refrigerants, HFCs are very popular. Now, HFCs they have zero ozone depletion potential, but they have global warming potential. They contribute towards the global warming. Now, I will explain you how this ozone depletion potential and global warming potential are gauged. The global warming potential of CO2 is considered as 1. Ozone depletion potential of R11 is considered as 1. Relative to these chemicals, the ozone depletion potential and global warming potential of other chemicals is judged. So, now here is a table which is showing the ozone depletion potential and global warming potential of different refrigerants. So, R11 and R12 they are not being used anywhere. However, they have the ozone depletion potential of the order of 1. R22 has a limited life. I mean, in advanced countries, the use of R22 is permitted up to 2020. But here in the third world countries, we can go up to, we have got a grace period of 10 years. So, we can use R22 up to 2030. It has ozone depletion potential only 5% that of R11. But now the issues are related with the global warming potential. And R134A is also contributor towards the global warming. The best refrigerant is, you can see, ammonia, R717. Ammonia, R717, if we look at this refrigerant, it is absolutely environment friendly. It has zero ozone depletion potential, zero global warming potential. Toxicity is high in ammonia, and that goes against the use of ammonia in many of the applications. New refrigerants like R1234YF, this refrigerant is new in the market, which has very low global warming potential and no ozone depletion potential. But this refrigerant is slightly flammable. So, some flammability related issues are there with this refrigerant. Now, in many areas, R77 use of R744, R744 is carbon dioxide. The use of carbon dioxide is explored. The global warming potential of carbon dioxide is 1 only and ODP is 0. But carbon dioxide is a high pressure refrigerant, but still the possibility of this use of this carbon dioxide in mobile air conditioning is being explored. Otherwise, because this carbon dioxide cycle it turns out to be a transcritical cycle. If we use at a normal temperature, it becomes a transcritical cycle. But for low temperature applications, this R744 can be used. That is all about the refrigerants in this lecture. And from the next lecture, we will start with the absorption refrigeration system. Thank you very much.